Mhm. Yeah. We are now recording. Hello, everyone. Uh, yeah, so you guys can see there, right space. All right, I finished grading your homework one, Weka. So make sure to look at that. If you have any questions, it was two classification, one regression, but if you did three, it's fine. It's your first homework assignment. Um, as long as you remember, it's not about the scores necessarily because that depends on the problem that you've selected. It's about just, the process, the pipeline. By the end of the semester, hopefully you'll learn. It takes, some work to get the models to work. All right, so yeah, so you guys are section three. Today's Tuesday, week 5. So I remind you that you have exam one a week from today. Okay. Remember, it's closed notes. You'll be taking your exam here in class. You're allowed your cheat sheet though, an 8.5 by 11, and you can write whatever you want on it. You can use a magnifying glass. All right. So yeah. So today we're gonna do a new topic, which is naive Bayes. Should be very interesting. Does have a bit of math, but I will try to cover everything in a way that pretty simple and intuitive. Give you the background. Okay. It'll be like it's really like two lectures because it's two cases. Okay. So we'll go over that. And it's the topic of naive Bayes. So obviously you've been using naive Bayes already. You know it's a machine learning algorithm. Um, and so, all right. So let's go ahead and click on here. So this will be the whole week. We'll cover naive Bayes. It'll be on the exam, but no homework for this one. Next week the exam, and then we'll probably start on Thursday singular value decomposition, which is also geometric based. Pardon? Yeah, the exam is on Tuesday, yeah, a week from today. The Thursday I'm gonna start probably a new topic. So you've used SVD in your k-means clustering example. So you've used it, but I'm gonna start introducing like the background, the algorithm, and so on. So that's called singular value decomposition. Is an extremely powerful technique used for so many things. It's like crazy for how many things it can be used for. But in particular, we've used it for compression. We'll use it actually. We'll view this topic in regards to recommender systems, which should be interesting and fun because we live in a world where we get bombarded by recommendations right online of things to purchase and so on. But yeah, so that'll be um, in a week on Thursday. This week we're just going to focus on naive Bayes, as I said, which is also very interesting as an idea, and it's not it's a family of algorithm, not like geometric, algorithms or like neural networks, but it's its own, right? Or trees for that matter. It's its own class based on probabilities, right? So very interesting idea. Probabilities essentially. So you've taken a stats course, for instance, or you will, and I'm sure you covered probability there. And it's kind of the same idea. And I'll introduce everything. We'll do it in code, and it should be pretty straightforward. So we have covered these topics. And as you can see, we are here in naive Bayes. Yeah, so I'm going to click on it. So you guys are section 3. Yeah, so I'm in section. Okay, and so here today I'm going to, write on the whiteboard. So I'm going to make some notes. I have my notes here already. I posted, so everything that I'm going to write on the whiteboard is already on this PDF. You can take a look at it. I provided the code here, but I actually did make some updates this semester, so I'm going to provide the update. So it's in Machine Learning Foundations. It should be base, right? And it's everything you see here. So I added this README this year, so it should be pretty helpful. And we'll go over this today and Thursday. And this is the algorithm that we're going to cover, the exam. All right, so let me copy this. Copy. So make sure to read everything there, please. And KNN, so we're in the right order. So let me just add a link. I'm just going to call it code base create. All right, so that has been added. So we can go back to the table of contents here. Naive base, yeah, so we're in the right place. All right, so yeah, we're gonna get started with this idea. I need to motivate it. It's gonna build on several of the ideas that we've already covered from the clustering example. I'm gonna use language so there's two cases, the discrete case and the not discrete case, the numeric case. So we'll take a look at that. So we can click on code here. So sometimes one is called the multinomial, the other one is called the Gaussian. Essentially, case one, text classification. So I'll explain this first. And then we have the continuous case. So essentially, sometimes if you have a word, right, you have a word like cat. How many times does cat appear in a book or several books, right? So you can count it. That's a feature, as you know. Versus iris, the iris data set, right? You have sepal length is 2.1. How many times can you count 2.1 as a value? You see that, or sepal length essentially. How many times can you count that? So instead, we just have a measurement, right? So that's the difference. All right, so we'll see that the two approaches. All right, and although the equations seem complicated, they're not. You'll see that. So let's take a look at. So let's switch over to the whiteboard. So we're going to go to the whiteboard, new whiteboard, classic. All right, here we are. And like I said, all these notes are already posted, right? So yeah, so in this case, this should take like an hour, the first hour. It's pretty straightforward. The topic is naive Bayes, right? So naive Bayes. It is definitely the best example to get the intuition because it's really something that you can actually understand and implement on your own, right? So this could be a homework assignment, or you can just do this for fun if you'd like. And I provided code examples, obviously. Yeah, so we're talking about the naive Bayes algorithm, and we have to remember that our data, right, usually is represented like this. So we'll have, and this is a supervised learning problem, right? So that means we have classes, right? So for instance, for the iris data set, we have 3 classes, Setosa, Virginica, versicolor. So this is that type of problem, okay? That hasn't changed. Remember that we're going to have features F1, F2, F3, ... all the way to Fn. So sometimes you can also write these as X1, X2, X3 to Xn, right? Just in case I change my notation, but that's essentially the idea. All right, so the goal with naive Bayes is essentially that every feature gets a say in determining which label should be assigned by the classifier. All right, so the goal is to kind of look at the features and then do some calculations, and then based on the features, you say, oh, okay, I calculate that the probability that these features belong to this class is this much, 12% versus 15%. And then you just pick the highest probability. Do you guys see that? So that's essentially the idea. So for this case, the discrete case of words, that's what we're gonna do, right? So in this example, it's gonna be language based. So it's going to be essentially, let's say words and documents. And I will motivate kind of, for this case, the variables that we're going to use. We'll need to define like the scope and what things are. But essentially, in this case, naive Bayes, the discrete case, if you will. Discrete just means like when you have things like words, etc. Naive Bayes uses the frequency of each label in the training set. So we're talking about frequency counts. Okay, so essentially just counting things. So frequency counts. Right, so you would just go in through the algorithm, find this word in this document with this class. Okay, count it. Then count it again, and you just keep counting. And then you just have like a table of all the counts. Do you see that? And that's essentially the approach for this case. And like I said, let's call it case 1. Because I do feel this one is the more intuitive. Not that the other one is hard, but this is like the more intuitive to understand the algorithm. And then we'll look at the next one. Right? So essentially, remember I said naive Bayes belongs to a family of algorithms based on probability. So this is not the only algorithm we will cover from the family of probabilities. There will be at least another one called hidden Markov models, HMMs. Very interesting, very powerful algorithm for sequential things. So for instance, for those of you that like Bitcoin or the stock market, right, you need to predict sequence of predictions. Monday, Tuesday, Wednesday, what's the price of Bitcoin on Saturday, right? Given the sequence. So that's a hidden Markov model is native to that kind of problem. And that's going to be probabilistic as well. But, we're not going to cover, I'll cover it later in the semester. But it builds on this foundation. All right, so probability, right? So what's a probability? Essentially just, a value that you say, right? So very simple. Out of 100 cases, 73 were this or that. And you use that as reference in the future when you make a decision. So yesterday, it was cold, right? And so what's the probability that people were going to have ice cream? But today, or yet, maybe let's say last week was really cold. What's the probability that people were going to have ice cream versus we're having like warmer weather, right? So what's the probability that people will have ice cream today? Maybe one of those Mac cafes that are icy, right? So more likely, right, based on the information. So that's essentially what that is for. To make those kinds of calls, you just keep the probabilities, okay? So this example, as I said, it's language, natural language processing. So we're going to have, and it's a classic example actually in information retrieval. So this was a big thing. We're going to imagine that we have a company, like a publishing company, right? And we have all these magazines that we manage, like 1,000 magazines. And what we want to do is we want to like classify these magazines. Are they science fiction, but are they also funny, but are they also sports and science fiction? You know what I mean? So creating like labels of this so that readers can find them, and then maybe they'll want to subscribe to our service and pay more and all that. All right, so that's going to be the motivation for this example. So we're going to have words and we're going to have documents. Okay? So documents. And I need to define these, right? But this is going to be like our medium, our data set, etc. All right, so let's give this some definitions for this case. So let's say that we have 100,000 documents. 100,000 documents. And just to give it a value, let's say that each, something that's understandable, every document has 2,000 words. And this is a document, maybe to keep it simple, it's a TXT file. And it's, we say that we have 2,000 words. 2,000 words per document, okay? So we have, something like that. All right. Also, we've talked about vocabulary, and we talked already about the bag of words approach, right? So we can use that as an idea. So the count vectorizer, if you remember, we already used this one in our k-means example. Similar concept. We are using the bag of words approach. The bag of words approach. So that means we need to define a vocabulary. Well, if we have 100,000 documents, that's a pretty large vocabulary probably that we need. So let's say usually, believe it or not, things like ChatGPT, etc., have a vocabulary of about 50,000. Although it's not words, instead it's something called a subword, which is more similar to a syllable, except that it's a syllable not like humans create, but based on statistics, right? Based on probabilities. So the algorithm called BPE creates it. But essentially it's like syllables, parts of a word, and the vocabulary is about 50,000, 50K. Okay? So we're going to just go with that number, but here in our case, it's going to be words. Let's keep it simple. All right? Yeah, so that just defines the problem. Then let's think of some ideas here. So we have categories, right? So we have it's a machine learning, naive Bayes, as you guys already know. You've used it in your homework assignments, etc. It's a classifier, so it's got classes. So for instance, we're going to have for magazines classes like sports, right? And let's say that's 12%, right? And then we can have like mystery novels, maybe. 3 novels. Let's say that's 10%. And let's say we have like aviation, specialty. That's just 2%. So the key intuition here is that a document about aviation, right, will have specific words related to aviation. So for instance, here I have a word like aileron. Right, so aileron, of course, it's more likely to appear in the context of aviation. So we're going to have a probability of the word aileron associated with aviation. Now, is it likely to appear in somewhere else? Yeah, aileron could be like John Aileron or whatever, so like a nickname maybe. So it could appear also in sports, but it's less likely, right? Do you see that? And so that's kind of the intuition there. So this gives us, for our case, some ideas. Okay, sorry. So page 3. So that's essentially it. So things we know about naive Bayes. So usually the worst performance, right? So we've established that in terms of precision recall F measure. But it serves as a baseline, which is not bad. It does have advantages, like it performs really fast, right? So, something like calculating probabilities of things is also parallel, right? So you can calculate things in parallel, do counts of different books in parallel and then combine it and things like that. So it's an algorithm that you can run in parallel, and it's very fast. It's good with memory management, etc. But the performance is not always the greatest, at least in naive Bayes. All right, so what is naive Bayes based on? And what are these, this family of probabilistic machine learning algorithms based on? So essentially, a lot of these algorithms are based on something called conditional probabilities. And that's just a fancy term that's actually quite simple. Okay, and that's why we are doing this example with counts, because we'll see what that means. So we can interpret it in words easily without getting too complex. But it is based on a principle called Bayes' rule. And that's one little equation that we will learn. And just, we don't have to learn the derivation or how it came about. We're just going to use it, right, and know that this is pretty important. So there's somebody named Bayes that came up with these ideas. But there's, an equation, essentially. So the goal is going to be that we want to predict the class given a document. That's really the question that we're going to try to answer in this problem. So I have a document, right? That's my input, my sample in a vector space. Imagine that's my point, right? And so I'm going to receive that document, and I want to say it is sports, mystery, aviation, or something else, right? So that's essentially the idea. As it turns out, calculating this is hard, right? So Bayes came up with this idea. So we need to define that D means document. D means document, and of course C means just the class that we're trying to assign. So Bayes said, okay, calculating this like this is hard to think about. But he came up with this equation that works really well that says, well, we can simplify some of these terms, but just perform several computations. So Bayes' rule then is rewritten, or is written as, instead, we want the probability of class given the document. Instead, he said, why don't you calculate the probability of document given class, which is a little bit easier to do, times the probability of the classes in your data, divided by the probability of the document. So you can see he's simplifying, right? Just calculating how many documents you have of this class and so on, how many classes, and how many documents. And so this is essentially Bayes' rule, okay? So this equation here. So we need to compute this formula for all classes. So for instance, we're going to have a situation where we're going to say CI. So essentially, if you have 3 classes, you're going to do this computation 3 times, 1 for each class, and then you're going to have 3 probabilities. Do you guys see that? Once you do all the calculations, and what do you do then? You pick the class with the highest probability. That's essentially the main idea. Make sense? All right, so you were going to do this for class 1, then do this for class 2, then do this for class 3, and then whichever one is the highest probability, that's your selected class. So that is Bayes' rule. So the classifier then can be written as follows. So we're going to select, right, the class. We're going to say argmax, and remember that you guys, we've talked about argmax in the first 100 problems that you guys are working through. Argmax is a very nice equation, it's a function. It's similar to in KNN, right? And KNN, we did this also. Remember when you have something like 0.20, 0.4, 0.15, right? So we select what? The index of the highest value. So here I have indices 0, 1, and 2. So this one has the highest probability. Therefore, what I would get is not the value itself, but the index, right? 1. That's what argmax gives you. And so in this case, essentially, we're going to calculate for every class the probability and then select the class with the highest value, right? And we will see that. So then we write this as argmax of P, C, given D, right? So given the document, what is the class? But remember that because we have this Bayes rule, right, we can rewrite this equation then as argmax, and then we're just going to replace this. So P of D given C, all right? So we just flip these, times the probability of C divided by the probability of D. Probability. And I need to define all of these things, but this long story short is it's a frequency count of all the words, of all the documents, and so on. Okay? And this is, remember, a classifier and the algorithm. So this is our classifier and the algorithm. So now let's expand this and let's imagine how this works. So we have 3 classes, let's say. So we're going to do C1, C2, C3. And remember, this is really, because it's more convenient to work with vectors and matrices. This is just going to end up being a vector of size 3, and then we can just use argmax on it. So if we have for C1, we just have, like expanding it. So we're saying argmax for all 3, but I'm just going to write it like this. Probability of D, and this should be pipe. So given C1. So what is the probability of document given that the condition that it is class 1? Right? So we need to have this statistic times the probability of C1 divided by the probability of D. Do you see that? And remember, we're doing this for the same problem, right? Same data set. Then we repeat this, argmax. All right. Probability of that. What is the probability of this document given C2 times P C2 divided by P D, right? The probability of D. Probability of D. And then the third one, D3. So argmax, right, of all 3. This is going to be, we need to calculate the probability of D given C3, right? So we're going to need to have a table with these probabilities. When it's class 3 times the probability of C3 alone, and we'll see that in a second, times the probability of D. So as you guys have seen in machine learning, it's a lot of calculations, sometimes a lot of data collection, computation, right? And sometimes these things can be expensive. Now, another thing that's important is sometimes with these algorithms, you make a lot of simplifications, right? And as it turns out, even with the simplifications, they do work well. So one thing here that we can see is that they all have in common PD. Do you see that? So essentially, because they all 3 have in common PD, that's a term that we can actually cancel out. Do you guys see that? Because we would, that's like a constant, so it's not going to affect the final value. And so we can cancel this out, and essentially then the final result becomes just argmax probability of D given C times the probability of C. And this becomes simpler, right? So now we've simplified the algorithm. This is not something that you guys have to do every time, right? You just use the algorithm as is. But I'm just showing you that it comes from this idea of the Bayes rule, but the Bayes rule, as you expand it, you can cancel out certain terms, right? And we will see we still need to make some assumptions as well to simplify things. Okay. And this applies to both the discrete case and the real valued number case. All right, so this turns out now to be where we are in our naive Bayes algorithm, right? So we've simplified it. We've got rid of probability of documents. Now we don't have to calculate those probabilities. Saves you time, computation, etc. So now let's think a little bit about, go back to the document, because we need to now, you can see the document is in there still, and we need to define what that is, essentially. What's a document, right? So that, what you guys know about machine learning is you need features. So how are you going to do that? So we have a document here, and let's say we have, it's a file, a little rectangle, right? And, we have a sentence, the car is. All right, so we know it's 2,000 words. So we need to represent the document as features. And we're going to use the bag of words approach in this example. So this is similar to what we did like in the clustering example. So now we're going to need to rewrite our function, right? This one, Pd, needs to be rewritten. And the only solution is that we're going to represent the document as a vector, right, of words, correct? And we know that we have how many words? 50,000, right? 50,000 words, 50K. So same idea, right? So how many times do you see the word car in there? One, maybe. How many times do you see the word cat in there? Two. But the rest, if you guys remember, are zeros, right, in this type of representation. So it's still a very sparse vector, okay? So that's what we're doing. So remember, this is the type of data that we have available here, all right, as the features. So that means that we're going to need to represent the document as that, right? And we can refer to these as the features x1, x2, dot, 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 all the way to x, let's say n or 50K. So we're going to need to rewrite this function here in terms of that. So we're going to go back here and redefine naive Bayes to be C, the class argmax, but now it's going to be the probability of x1, comma, x2, comma, x3, right? Because a document is really made up of all the words, so we have is a set of words, dot, 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 comma, xn. So what is the probability of that given C, right? So that's how we wrote it, right? You can see I'm rewriting it. Probability of document given C. Now the probability of the features themselves given C times the probability of C. So these will have specific terms. This is usually, and I'll use a different color here. This one is usually called a priori. So this is called a priori. And you'll see this in the code, and this is just, terminology that is used. And then this one over here may be called a likelihood. Okay, so these are the terms that we will see in the code. Okay, so each of these two terms. So these are multiplied here. Okay, any questions? Remember, these are the features that we're used to. So we can call them features and so on. Okay, so now the interpretation of PC, for instance, so we can talk about this one. So the interpretation of PC, we can say how often does this class occur, okay? And this is really important in probability. And sometimes this is lost on when you take a probability course or something, you just look at the numbers and things like that. But it's very critical that you develop like a language of how you interpret things, because this can be then very clear. So how often does this class, aviation, occur? So does this class occur? Okay? And again, how often just means some kind of a frequency count. Okay? So that's the idea. Any questions so far? All right, so now before we continue, one thing that we have to consider is how do we get these frequencies? Well, we're going to count the frequencies in the data set, right? So we would have some kind of a data set, 100,000 documents already annotated, right, with classes and so on. And so we have to compute these, and we'll define that at the end. But one important assumption still needs to happen for this to work. So notice that right now, this is like jumbled. It just means, okay, all the words in that document are the representation, But really, we have to make a simplification for this to work. So here, what naive Bayes does is it makes an important simplification that is best illustrated like this. So I'm going to say I have two sentences. One is the car is going fast, and I have another sentence that says the fast car is going. So as you guys can see, the sentences have the same words, but they are actually different semantic meaning, right? You would agree, like the fast car, it's something like a Formula One car, right? Something like that, a fast car. Versus the car is going fast. I mean, what's the slowest car that you guys can think of, right? Like a pickup truck or something, right? So, you know, it can still go fast for, relative to what it is. So you guys can see that they have different semantic meaning. But when we represent them in this naive Bayes, we're gonna lose order, right? So for instance, I'm gonna use a vector car going fast, and I have another one, car going fast. Really, these words are in both, so you're just gonna get a 1, 1, 1, 1, 1, 1. Do you guys see that? So you're gonna lose some information, and you have to make these assumptions. And the fact that you lose that information is pretty important, right? So, the fast car is going, Formula One, sports, right? That's, makes sense. The other one, the car is going fast, maybe that was just some news article, something else, wasn't sports, So there's important meaning there. I'm giving you this example because you have to assume that we make assumptions. And one of the big assumptions that we have to make in naive Bayes is that we have to assume that we get rid of order, and we have to assume currently this thing here is a set, a fixed set, right? Dependent. It's one thing, a whole, but you can't compute that, right? You cannot compute that. What you can compute is the probability for each word. But if you calculate the probabilities for the words themselves, then you have to assume that they're independent. Otherwise, it would be very complex to compute the probabilities that are kind of like mixed up, this word with that word and so on, right? So we have to simplify this. So we make the assumption, we assume that the words are independent. The independence assumption is really important. So are independent and this is a huge assumption in naive Bayes, right? And actually this is not true, right? This is not true at all. But even in iris, right? In the iris data set, sepal length, sepal width, I mean, they're related, right? Petal length, petal width, sure. I mean, there's some kind of obviously it's the same plant. But naive Bayes is saying petal length, not related to petal width. Sepal length, not related to sepal width. It's a huge assumption. And this is maybe one of the reasons why, in terms of accuracy, naive Bayes, it may not be one of the best algorithms, yet sometimes it does work, right? So that's the reality. And so naive Bayes is a great example of learning that machine learning algorithms have to sometimes make lots of simplifications. All right, or assumptions, as they are called. So now we are ready then to rewrite our very complex calculation of probabilities that were like intermeshed into probabilities that are independent. And wow, at that point, if I gave you this homework, right, without giving you this independence clause, you would have a hard time. You'd be like, how do I calculate fast car going? It's complex, right? But now I'm making your life easier by simply saying, no, treat them as independent. So now you just calculate for every word the probability of it and nothing, in relation to the class and the document, but not to the other words. Makes it a lot easier. So now the algorithm becomes, so remember, it was something like this: probability of x1, x2, x3, dot, 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 xn, given the class, right? This is what we were calculating. But as I said, this is pretty complex. That would not be fun. In fact, some of you would probably just say, without me even saying this, you'd be like, after a while of trying, I'm just calculating them independently. That's what I'm doing because it's easier, right? And so, as it turns out, when you treat the variables as independent, this can be rewritten in a much nicer way as the probability of x1 given class, right, times the probability of x2 given class times, and I'm just going to continue down here, say dot, 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 times, dot, 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 the probability of x3 given class times dot, 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 the probability of xn given class. And then also remember that, I'm just including this term right now, but that's it. Do you guys understand? So this is a huge simplification, but it makes your life so much easier because now you can just focus on finding the word cat and what is the probability of cat given the class in the document. Now find the word aileron. What's the probability of aileron given the class in the document? But you don't have to take into consideration aileron and airplane and all that, right? So it's a huge simplification. So now that we have done this, we can rewrite the base function as the following. So we can say argmax, and remember, I'm going to go back to here. So I just made this independent, right? So every x1 is now independent. This is a series of little probabilities, and times PC, if you remember, which was the priori, and that's how often does this class occur. Okay, so don't forget about that. So I'm going to deal with PC first, just so that I don't forget it. So here you can see I'm moving it. PC, this is the priori. Okay? And then I'm gonna, writing this very long thing with all these dot, dot, dots is pretty complex. So there's a shorthand, more like a for loop, right? There's a symbol that you can use that looks like this that just means for, in a for loop, multiply all these terms. Okay, so it's just me rewriting it. So I'm just saying from I equal 1 to n, I'm going to take the probability. So notice that all of these are probability of x1 given c, probability of x2 given c, probability of x3 given c. So essentially I can generalize, as you would do in the code, to probability of xi given c. Do you guys see that? And I just rewrote this whole sequence over here as essentially this. And this is, remember, called a likelihood. But now they are all independent. Every every variable can be calculated independently as a frequency. And that's it. That's the algorithm of naive Bayes. What remains now is for us to define, exactly how you calculate these terms. Any questions, guys? And you would need to calculate all of these. And I did provide a code example in the note. So now the final question is, how do we get these probabilities, right? So we have to get these probabilities, and the answer is that you count the frequencies in the data. So we need to define now all of these, right? So we need to define the probability, we need to define the probability of C for each class, J. So what are those, right? How do we compute those? And we also need to define the probability of each wi, which is a word, given the class j, right? So we also need to calculate those. And this is something that, you'd have to go into your document set and you'd have to make all these frequency counts, and it's usually just numerators and denominators, right? And getting that fraction. So let's define first how to do the probability of class. So let me do the probability of Cj is going to be equal to, so notice I'm going to have numerator and denominator. I'm making this really big because I'm actually going to write it out so it's super clear. First, in the denominator, we need to have the count. We need to count. So the count of all the documents. So that's easy enough. We had 100,000 documents. There you go. Done. Right? So the count of all documents. Right? So usually your x is going to have that data. So x dot shape 0 gives you the count of all the documents. All right? In the numerator, I'm going to have how many of the documents, how many of the documents notice that this one, is just like this. How many of the documents are in class J? So here you'll see that in the code we can take a similar approach to the one we took for the k-means. Again, you can see how they're tied together. We just look in the y vector, look for class 2, right? All the values that are class 2, that returns the indices, right? That of those items that are class 2, and then we go to the x and grab those indices, and boom, we have our data. Okay, for how many of the documents are in class J. Any questions, guys, on this one? Pretty easy, right? All right, so we, shorthand for this one, I can just do class J. I like to write it out, but if you remember, you can just say n documents, and you can say docs per class J. Remember, in this case, let's say we have 3 classes, or you can have 15 classes. It just depends. But CJ. All right, so we've defined that term. Now, for the frequency count, for this case, right, remember this is specific to this case, not to all cases. When some cases we can't do counts. All right, so now the next one is, let's move to another page. All right, this is the other one. The probability, because now we have the independence assumption, this is a lot simpler to calculate. The probability of word I given CJ, right? So for every class, we have to get the word, right? And it's that specific word, and we just count how many times we see that word, and that's it. It's a lot of words, though, 50,000 or so. So you might have to do takes a while. But this is the kind of thing that, big companies, etc., Google will do in parallel. And that's why they have all those computers. Right? So here, let's define it. So WI given CJ. All right, I'm going to do the same thing as before. So notice here, whoops. So I'm going to have a numerator and a denominator, and because this is like in words, right, I'm going to use a lot of space. So I'm going to use a big description so it's crystal clear. So the numerator is going to be the count. So it's the count of how many times, count of how many times, WI, which is, WI would be cat or elephant, right? So specific word, count of how many times WI occurs in documents of class CJ. CJ. Do you guys see that? Does this make sense? So for those of you, if you've taken 372 with me, we did a frequency count with Hadoop, right? So it's, you use some software like that in parallel, but essentially this is it, right? So count of how many times WI occurs in documents of class EJ. So what do? You find the class 2, right? And get the indices, then grab the documents that correspond to that, and then out of those documents you look for the specific word and you count it as a frequency. Any questions? All right. And then for the denominator, we do total number of words. This is easy enough. In documents of class J. And this is the denominator. You get this statistic, and now boom, you're able to calculate the probabilities for all independently. So now you have all these probabilities for the likelihood, for the priori, and there you are. You can now use this formula here, which is your naive Bayes. And remember that you do it for class 1, class 2, class 3, let's say. You end up with one probability for each of the classes, and you do argmax. So essentially you would end up with say here you would end up with a vector like this, argmax over here, and you have a probability, let's say class 0, 1, 2, probability of 0.2, probability of, let's say, 0.4, probability of 0.10. So there you go. Your class is selected as 1, and that's it. That's how naive Bayes works. It's that simple. Sometimes just, as numerically, you want to have like a +1 here, just so that you don't end up with a situation where one of these is division by 0 errors or something like that. But that's hardly going to affect it. Just don't want the code to break. Does this make sense, guys? That is the conclusion of the naive Bayes algorithm for this use case of words where we do frequency counts. Any questions? Pretty simple, right? Pretty straightforward. Let me just check my notes to make sure I'm not missing anything. Yep, so that's it for this one. And so in conclusion, this is the formula here. That we use. And so that's essentially, if I asked you on the exam, what's the final formula for naive Bayes is this one. If I asked you derive the naive Bayes algorithm from Bayes rule, then you basically the whole lecture today, which, just a few statements. All right, any questions on this? Make sense? Okay, perfect. All right, so that's great. So we finished this case. So I'm gonna keep it as one separate video just so that you can focus on this one. So let me end this one here.